Equilibrium on a frictionless incline. A straight piece of conducting wire with mass capital M and length capital L is placed on a frictionless incline tilted at an angle theta from the horizontal as shown in the figure. So this is the incline tilted at an angle theta, and this is the conducting wire with mass capital M, length capital L. There is a uniform vertical magnetic field at all points, produced by an arrangement of magnets not shown in the figure. It's a uniform magnetic field pointing upward. To keep the wire from sliding down the incline, a voltage source is attached to the ends of the wire. When just the right amount of current flows through the wire, so there's a voltage source here, so that there's a current flowing, the wire remains at rest. Determine the magnitude and direction of the current in the wire that will cause the wire to remain at rest. Copy the figure and draw the direction of the current on your copy. In addition, show in a free body diagram all the forces that act on the wire. Okay, so this is the wire, and if the current flows to the left, you can see here L cross B, which will be found by pointing the four fingers in the direction of the current to the left and curling your four fingers towards the upward magnetic field B, then you will see that the force will be pointing into the page. So it is L cross B, the force points into the page. You can see that the force FB will point into the page. Okay, so right hand four fingers in the direction of the current, curled towards the vertical magnetic field, the thumb points into the page. In that case, this force will have a component in the on the plane of the incline, which will cause it not to slide. So it will be pointing upward in the direction of the inclination angle. So it will be pointing upward like this, and it will allow the wire to remain at rest. You see, if the current flows to the right, then you would have this force pointing out of the page towards us, in which case it would have a direction that will be coinciding with the component of the gravity that is trying to make it slide down. So it's going to not cause the wire to remain at rest. So with this argument, we can say that the current must be flowing to the left. Okay. So if I look at it from this point of view, you can see that this is the angle theta here, this is the inclined plane, and there is the gravitational force pointing down. So this is mg pointing down, and my force into the page will be basically looking like this. This is my magnetic force Fb, and the direction of the current is going to be, looking at it from this side, out of the page. So this is going to be the current coming out of the page. All right. And the magnetic field B points upward in the vertical direction. So this is basically showing me the direction of the magnetic field, which is pointing upward. With that, if I draw my x and y axis like this, x-axis coincides with the inclined plane, the y-axis is the vertical axis, the vertical to the inclined plane, this is my 90-degree angle. The force, the magnitude of the magnetic force the wire feels is IL cross B, so it's going to be IL B, why? Because the length vector L is perpendicular to the magnetic field B, so it's ILB sine theta, sine 90, which is 1. The vector form is I L cross B. L is the length vector in the direction of the current. If I look at the x component of these forces, the net force on the x-axis, which is basically this inclined plane, it's going to be, you can see from the geometry here, this is theta, this is 90, 90 minus theta, this is theta. mg cosine theta is the perpendicular component, mg sine theta points down the incline. So this is mg sine theta. On the other hand, the magnetic force makes an angle theta with respect to the inclined plane pointing upward. So it's going to be minus the magnetic force Fb cosine theta, and since this is to remain at rest, the net force has to be equal to 0. Now if I substitute for Fb ILB here, I will get mg sine theta minus ILB cosine theta should be equal to 0, which tells me that the current that I need for it to remain at rest will be equal to mg over LB tangent theta. So if I isolate the current here, mg sine theta over BL cosine theta, sine theta over cosine theta is tangent theta, so the answer will be mg over LB or BL tangent theta. Okay, so here I have the free body diagram basically. I'm looking at this wire as a point, okay, and you can see here my mg vector points vertically down. I just changed the direction accidentally. So this points vertically down. That's my mg, the weight of the wire. And the magnetic force points towards the left. It's found by L cross B. L vector is in the direction of the current. L cross B, right hand forefingers point in the direction of L, curl towards the magnetic field. The magnetic force, Lorentz force, points into the page. So from this point of view, it points to the left. And when I put my Cartesian coordinates here, the components of FB and MG perpendicular to the incline will be balanced by the normal force on the incline. But the component that is on the inclined plane, that is on the x-axis, those two components should be balancing each other for the wire to remain at rest. It's going to be mg sine theta pointing in this direction, ILB cosine theta pointing in this direction. So when I set it equal to 0, I find that the current is mg over LB tangent theta.